Welcome back to this series of lessons about dynamic branch prediction. In this lesson I will describe more advanced branch predictors than the schemes considered in the previous lesson. The first branch prediction scheme, more advanced branch prediction scheme, is local history branch prediction. It is based on the observation that many branches execute repetitive patterns. Consider, for example, the inner loop in this code snippet highlighted in red. The branch implementing the inner loop has the behavior taken, 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 not taken, and this behavior is repeated n times. In other words, its behavior is 1, 1, 1, 0, repeated n times. This behavior is so predictable that if we know the direction the branch has taken the previous 3 times it was executed, we can predict it with 100% accuracy. If the history is 1, 1, 1, then the prediction should be 0 or not taken. For all other histories, the branch will be taken the next time it is executed. A local history branch predictor exploits this observation using a table of local histories, which is indexed by the lower bits of the PC. And these histories are called local because they are per branch rather than the history of all branches. In addition, it uses a table of 2-bit saturating counters, which is indexed by the local history found in the table of local histories. Here's how the local history branch predictor works. Here's the program counter, the address of the branch instruction. The lower bits of the PC, in this case 1, 0, are used to index the table of local histories as shown here. Then the local history found in the table is used to index the table of saturating counters. This table is in fact identical to the branch history table with 2-bit entries that we saw in the previous lesson. The index entry is 1, 1, so taken will be predicted for this branch. Of course, when the branch is executed, both the table of local histories and the table of counters need to be updated. A 0 or 1 should be shifted into its local history, depending on whether the branch was taken or not taken, and the corresponding counter needs to be incremented or decremented. There are 3 reasons why this local history branch predictor can mispredict. The first one is that it simply produces the wrong prediction. This can of course always happen. The second reason is that other branches have the same PC bits and therefore map to the same entry in the local history table. The local history will therefore contain the history of all these branches. The third reason is that the history of other branches may be the same as that of the predicted branch, and therefore they map to the same entry in the table of counters. However, different branches might have the same history at a certain point in time, but have a different branch direction the next time they are executed. The next advanced branch predictor is global history branch prediction, or just global branch prediction for short. It is based on the observation that the direction of a branch often depends not only on its own local history, but also on the direction of another branch or other branches. Consider for instance this example. If B evaluates to true, the branch implementing it will jump over the then part of the if statement and will therefore be taken. But then not B will evaluate to false and the corresponding branch will be not taken. Here's another example. If B, A is set to 0. If A equals 0, execute statement S. It can be seen that if B evaluates to true, then the expression A equals 0 will also evaluate to true. So the direction of the branch corresponding to the second if statement is dependent on the direction of the first branch. The bimodal predictor as well as the local history branch predictor cannot exploit this behavior, since the prediction for a branch is made only based on its own history. This motivates the design of a global branch predictor. In this scheme there is a single n-bit shift register that records the global history. The global history is the directions of the n most recently executed branches. So every time the branch is executed, this register is updated by shifting in a 0 or 1. The global history is then used to index the table of counters. On this slide I explain how the global branch predictor works. As said, there is a single n-bit shift register that records the global history. That is, the outcome of the n most recently executed branches. Those may be executions of the branch itself or executions of other branches. Then the global history instead of some PC bits is used to index the table of counters. Here's an example. Suppose that at this point in time the predictor needs to predict the branch implementing B current. Suppose also that B current minus 1 was not taken and that B current minus 2 and B current minus 3 were taken. Then the global history register will contain the history 110. This global history is used to index entry 6 of the table of counters and taken will be predicted. Global branch prediction seems like a good idea, but unfortunately the results provided by McFarling in his technical report show that it is actually less effective than the simple bimodal predictor for small sizes of the predictor table. The reason for that is that different branches can have the same global history but exhibit different behavior. For instance, a branch with a certain history may be strongly biased towards not taken, whereas another branch with the same global history may be strongly biased towards the opposite direction, taken. How can we remedy this situation? One idea is to combine the global history with the branch address, that is the PC bit, somehow, so that different branches with the same global history no longer map to the same entry in the table of counters. I will present two branch predictors based on this idea. The first one is called global history with selected address bits, or gselect for short. In gselect, some branch address bits or PC bits are concatenated with the global history. The resulting bit sequence is then used to index the table of counters. Here's an example. In this example, one bit from the program counter, in this case 0, is concatenated with the global history, in this case 11, to form the index 011. This index is then used to access the table of counters. Since the count is 01, the branch is predicted not taken. Here's another way to look at gselect. This view used to be present in earlier edition of the textbook. In this view, the counts are not viewed as a table but as a matrix with 2 to the power of n rows and 2 to the power of m columns. Then n bits from the PC are used to select the correct row from this matrix, and m global history bits are used to select the correct column. For example, here's the matrix of counts. In this example there are 2 rows and 4 columns. So 1 bit from the PC is used to select the correct row, and 2 global history bits are used to select the right column. The count is 01, so the prediction will be not taken. Gselect has an issue, however, and that is that the global history also identifies the current branch a little bit. While it is possible that 2 different branches have the same global history, it is not very likely. So there is a certain amount of redundancy in the index used by gselect. As a result, some counters associated with a certain branch will not or hardly be used. To illustrate this problem, consider for instance the example that I showed when motivating the local history branch predictor. 2 nested loops where the outer loop with index I iterates from 0 to n and the inner loop iterates with index j from 0 to 3. This code can be translated to this pseudo assembly shown here. The branch labeled bj and shown in red implements the inner loop, and the branch labeled bi and shown in green realizes the outer loop. Let's assume now that we use a 4-bit global history register. That means that per branch 2 to the power of 4, 16 counts are available. Let us also assume that both branches have been executed several times, so that the branch predictor is warmed up and has learned the behavior of both branches. Now it can be seen that when bi is predicted, the global history will always be 110, 1110, since the previous 4 branch executions were 1 execution of the bi branch and it was taken, and 3 executions of the bj branch and it was taken twice and then not taken. If the global history is always 1110 when bi is predicted, then only one of the 16 counts available to bi is used, which is very ineffective. Similarly, it can be seen that when predicting bj, the global history is either 1101, 1011, or 0111. That means that only 3 of the 16 counts available to bj are used, which is again very ineffective. To fix this situation, a branch predictor different from gselect is usually employed. This predictor is called global history with index sharing, or gshare for short. Instead of concatenating the PC bits with the global history, it hashes them. In particular, gshare n/n uses the exclusive OR of n bits from the PC or branch address and an n-bit global history. Suppose, for instance, that the PC bits are 010 and that the global history is 110, as in this example. These 2-bit sequences are XORed, and the result, 100 in this case, is used to index the table of counts. Gshare has been shown to be a very effective branch prediction scheme, and it has been employed in many processors. For example, the AMD K6 and K7, the Sun UltraSpark 3, the IBM Power 4 processor, etc. I complete this lesson with a few words about the table size of gselect and gshare, and with an example in which gselect and gshare use different indices. First, it can be seen that gshare nn uses a table that has the same size as the table used by gselect n-m/m when m is less than n, or as the table used by n/m-n when n is less than m. Second, the table used by gselect nn has the same size as the table used by gshare 2n. Gselect nn concatenates n bits from the PC with n bits of global history to obtain a 2n-bit index. Gshare 2n on the other hand XORs them and therefore also uses a 2n-bit index. Finally, several examples of the indices used by gselect 44 and gshare 88. As discussed above, their tables have the same size, namely 256 entries. In the first example, the last 8 bits of the branch word address are 8 zeros and the branch history is 7 zeros and then a 1. The bits used by gselect 44 are underlined. In this case, gselect 44 and gshare 88 use the same index. Also in the second example, gselect and gshare use the same index. More interesting are the third and fourth example. They both have the same branch address, PC, but differ in the leftmost bit of the global history. In this case, gselect 44 cannot distinguish between these two different global histories, since bit 7 of the global history is not used to form the index, whereas gshare 88 can. This completes this lesson. Thanks for watching. In the next lesson I will discuss one more advanced branch predictor, which is actually a combination of the branch predictors discussed so far. In addition, we will have a look at the performance of different branch predictors. Hope to see you back.